Picture a complex microservices architecture. You trigger the deployment, and then immediately the system flashes red and shatters. Getting enterprise Java code to compile is the easy part. The true test of an application's architecture is its ability to successfully survive its own startup sequence. The symptoms are highly visible. The Java virtual machine crashes, throws a non-zero exit code, or hits an out-of-memory error before the application ever opens a port to accept network traffic. Developers frequently hunt for faulty environment variables or standard memory leaks when this happens. But the most insidious crashes actually originate from a breakdown in the internal framework chronology. Looking at our core JVM troubleshooting map, we can bypass standard crash metrics and lock directly onto the source of these timing issues, the Spring Framework branch. Specifically, we need to examine the engine driving every Spring application, known as the inversion of control container. Inversion of control is the exact mechanism that transfers memory management responsibilities away from your manual code and hands it over to the framework's automated system. Instead of hard-coding the new keyword to instantiate objects one by one, Spring reads your configurations and constructs an automated lifecycle graph. This delegation is efficient, but it creates a strict dependency on timing. If you write code that attempts to use objects before the framework has finished assembling them, you will generate catastrophic null pointer exceptions. Stabilizing a failing JVM requires a shift in perspective. You must stop treating the inversion of control container as a black box and start treating it as a strictly deterministic mechanical assembly line. The instruction manual for this assembly line is the application context. This is the master schematic Spring uses to parse and prioritize your components as the JVM boots up. The context cannot construct a sprawling enterprise application all at once. Doing so would create unresolvable logic paradoxes. It has to execute the build in a highly specific, linear sequence. This graphic shows that sequence, known as the Spring Bean pipeline. Every managed object in your application must pass through these three distinct stages to reach a functional state. Stage 1 is instantiation. This is where the JVM allocates raw heap memory for the object. Stage 2 is dependency injection, often seen as auto-wiring. Here, Spring populates the object's properties. Stage 3 is initialization, which allows for custom post-construct execution. Attempting to collapse these three steps into a single simultaneous action is the architectural equivalent of a short circuit. It is the core reason why complex deployments fail on launch. To see exactly how that short circuit happens, this visualization isolates a single component, Bean A, as it enters the first stage of the pipeline. The scanner detects the class, triggering phase 1. The JVM invokes the empty constructor to allocate heap space. Bean A now exists in memory, but it's a naked object, entirely devoid of external connections. Assume Bean A must query a database, requiring a repository object named Bean B. A frequent error occurs when a developer calls Bean B's methods directly inside Bean A's constructor. In phase 1, the framework hasn't mapped connections yet. To Bean A, Bean B is completely invisible. The mechanical result is absolutely immediate. The JVM throws a null pointer exception, which violently terminates the entire application startup sequence. This isn't a class not found exception. Bean B exists on the class path. The framework simply hasn't had the chronological time to wire it yet. When operating under inversion of control, a constructor's only valid job is memory allocation. It should never contain business logic or attempt dependency resolution. Returning to the diagram, our naked Bean A advances to phase 2. Spring looks for the auto-wired annotation, signaling it to resolve dependencies. Behind the scenes, it locates Bean B's memory space and injects it directly into Bean A. Why architect the framework this exact way? Why force the strict separation of memory allocation and dependency injection? The answer lies in handling circular dependencies. This occurs when Bean A requires Bean B, but Bean B simultaneously requires Bean A. If Spring attempted injection during phase 1, Bean A would halt its construction to wait for Bean B, and Bean B would halt its construction to wait for Bean A, creating an immediate deadlock. By separating phases, Spring allocates memory for both objects first, ensuring two naked beans exist. Because both memory addresses are now secure, Spring can safely inject a reference of naked bean A into naked bean B, resolving the loop without a crash. Phase 2 property population acts as a structural safeguard, allowing massive, interdependent enterprise object graphs to resolve dynamically. Here in the final stage of our diagram, the fully wired component advances into initialization. Now that the object is built and wired, developers need a place to safely execute custom startup logic. The framework provides the post-construct annotation. This serves as the designated callback method for executing custom initialization routines. The structural guarantee of this annotation is absolute. Any code executed inside a post-construct method is guaranteed to have all of its auto-wire dependencies fully resolved and active. This is the correct location to execute logic impacting JVM performance, such as running a database warm-up script or preloading a cache to reduce initial request latency. The operational rule is straightforward. Business logic that guarantees a null point exception if placed in the constructor will run flawlessly when placed inside a post-construct boundary. Transitioning from a single bean to the macro reality of an enterprise application, we see this process operate at scale. This completed, interconnected structure represents your application's component diagram in its fully realized runtime state. The sprawling complexity of a Spring Boot application is merely the recursive execution of this strict, three-step lifecycle across millions of nodes. Which brings us back to resolving initialization latency and JVM observability. When investigating startup crashes or confusing non-zero exit codes, your first debugging step should be mapping the failing code against this specific timeline. Enterprise system stability is achieved when developers stop fighting the framework's chronological boundaries and start architecting specifically for them.